Okay, good morning, everyone. So I'll be mostly talking about the distributed deep learning. Essentially, this is how to parallelize your code to make sure run on our system. I will probably just give very brief introduction about the concept of distributed deep learning, and mostly I will focus on the lessons that we learn. And of course, there's a need for distributed training because of the model become larger and larger, and the amount of compute involved in the model, it's grow exponentially. And there's a plot by OpenAI. Usually, I said it in my talk, is that every 3.5 months, the amount of compute doubled for training in the AI model. And if you compare to the Moore's law, which is 18 months, double each time, and this is essentially 5 times, right, faster. So the amount of compute, it's growing 5 times than the computing resource. So that's why we need to do things in a large scale way. And of course, recently these large language model become kind of larger and larger, also introduce a challenging. And this the right side plot shows that almost like 10x increasing in terms of the number of parameters involved in a large language model every year. So now the largest model exists in the literature is in a trillion number of parameter. And in terms of training time, you can see, for example, I take out the table from this paper. I highlighted 3 columns. The first column is the number of parameter, right? So here the model is 500 billion parameter, and this column is the number of GPU that you used to train this model, and then this one is the days, the time, training time. So the unit is in the days. So basically, if you use 1,000 GPU to train this 500 billion parameter, you already take in the order of 100 days, right? That means that if you use 1 GPU to train this model, you cannot finish that in your lifetime. So that's why it is so crucial to use the distributed training to reduce the time to solution. And so this is the kind of brief background or the motivation why we need this distributed training. And then in the following, I just will go through some simple concept, and then I will also talk a lot about the I/O and data management, because I work a lot on this and learned some lessons that is good for us to know. And in terms of parallelization schemes, basically have 2 kind of characteristics. One is a model parallelization. Essentially, the concept is very simple. You have a big neural net, and we just partition the neural net into different pieces, and different worker here is the kind of different GPU. So you different workers work on the computation involved in the set of neurons that associate to distributed to it, right? And then of course they have a communication. So for example, the worker 1, the output will be sent to worker 2 and worker 3. And so this is the model parallelization. Another one is called data parallelization. In this case, each worker will have a complete set of the complete instance of the model, right? So all the computation involved will be inside of the single worker. The only thing that is the different worker work on different subset of the data set. And then during the training, they have to sync up the weights and gradients after each step. So So this is the model parallelization. In the traditional HPC, this is kind of similar to task parallelization, and this is the data parallelization is very common in the traditional HPC simulation. And compare these two parallelization scheme. I put on some comment on these two cases. The green means that it's a pro for this scheme of parallelization. The red means that it's the cons. So the model parallelization, because you split the model into different pieces, right? So imagine that you have a large model, the LLM model you cannot fit into single GPU, then you have to use this model parallelization, right? So this particularly useful when you have large model. And nowadays, people are kind of more and more focused on this model parallelization because of the because we are dealing with this LLM model. And in terms of the communications, essentially the worker are just communicate with the nearby workers, right? When this, for example, worker 1 communicate with worker 2 and worker 3 because they have to send the output to worker 2 and 3. And then the cons are this work for kind of simple model, like easier to partition, to divide the neurons, right? But if the model is very complicated, it's very hard to have a standard way of distributing this subset of neurons to different workers. In a sense that it is very hard to load balance among the workers. So there's a not standard scheme. So always it's a kind of state of the art. You just look at the model and then figure out the best way to distribute the neurons. And compared with this model parallelization, data parallelization, it has large memory footprint because you basically put the entire model into the worker. So it has a limitation, right? And then also the communication involved is a collective communication because all the worker have to sync up the weights and gradients, etc. So this communication overhead will kind of set a limit on how many workers that you can scale up to. But it is very easy to implement. You just distribute this the data, which is very easy, and it's load balanced because all the workers are working on the same thing, right? Of course, nowadays people combine these approaches. So say that you have a LLM model, you can distribute through the model parallelization up to, like, for example, 1 node, 4 GPU or 8 GPU. Then going beyond that, you can do the data parallelization. So it's a kind of practices that combine these two together. And then besides this kind of model parallelization and data parallelization, nowadays also a very common scheme is a pipeline parallelization. I will skip the detail about this. I just put this slides here. If you're interested, you look at all the paper. This is a particularly useful for the large language model. Training is large language model. So basically, in this training LLM model, you have to use like model parallelization, pipeline parallelization, and then this data parallelization together in order to scale to large number of GPU. So this is a kind of very simple background. And there are a lot of technical details that regarding the data parallelization, etc. I will direct you to the talk that I gave in the Apex training in August. I have a detailed kind of a theoretical description, introduction about all the distributed training. So in this talk, I will just keep it very simple. And then in terms of the distributed training frameworks, currently the popular schemes are Huihuo, DDP, and DeepSpeed. Huihuo is very general. It supports like TensorFlow, PyTorch, Keras, MXNet. DDP is building in the PyTorch core, so it only supports PyTorch. And if you are using PyTorch, you can also use DeepSpeed. And this is DeepSpeed is very common. It's designed initially for training the natural language model. And all of this framework are available in the kind of module I listed here. So if you load the module, activate this environment, then you have the Huihuo PyTorch, Huihuo DDP and DeepSpeed. If you want to learn a little bit more about this implementation, etc., you can check the link here. And then just briefly mention a little bit more about the data parallelization. I have some hands-on example provided in a GitHub repo, which I won't go into this example on this talk, but after the talk, you can feel free to play with it. And then this afternoon, I will be available if you have any question on that. So all those examples are data parallelization, data parallel training. So this just give a little bit more detail on this data parallelization. So essentially, what the data parallelization is that you have multiple workers, and each of the workers have a instance of the model, right? And here I show like 3 workers, and then you partition the data set into 3 chunks, and each of the model work on the subset of the data set. And each time step, it have the forward pass where you send the input and calculate the output, and also calculate gradients. This is called forward pass. And then in the backward path, during the backward path, you have to average all the gradients. And so this is the communication involved across all the workers. And then you do the update. And all of this averaging, the weights, gradients, etc., are done inside of the distributed training framework, either Huihuo DDP or DeepSpeed. So we don't have to manually implement this averaging process. Of course, if sometimes people want to know the average like loss accuracy during the training, right? That in that case, we have to do the manual averaging. And you can see the example in the code. And however, also I just list a few steps, a crucial step to changing a non-parallel code into a distributed code. These are the steps. Basically, I have 3 colors highlighted here. The first one is kind of initialization. The second one is more during the backward process. It's more involved in the communications. So the key part is that when you do the distributed training, the learning rate will be changing, and then the batch size is also changing. And so this learning rate and batch size will need to adjustment during the training. I have another few points that I want to mention later on after going through this. And then it's also important to this optimizer, wrapping the optimizer with a distributed version. This is to make sure that in the backward process, they will average all the weights and gradients. And then in the beginning of the training, we'll broadcast the weights from one of the workers to all the workers to make sure that all the workers start from the same point. And in terms of the checkpointing, we want only the worker 0 save the checkpointing files. This is the kind of for traditional data parallel training. And nowadays, when you do model parallelizations, you have to kind of checkpoint from each kind of worker, because it is the worker 0 doesn't have the entire model, right? So if you do model parallelization, you have to make sure that checkpointing or the entire model. So it typically involve multiple worker, multiple kind of GPU writing the data. So this is practices that is done when you're training language model. Then also the data set, make sure to distribute, to divide the data set into different subsets. The examples are provided here. the detailed instruction, like how to achieve all this point in TensorFlow, in PyTorch, or here. And then I also provide a code here. I also have the example on DDP and deep speed. You can check the folder in the GitHub repo. This just a few points. I mentioned that when you do the distributed training, you need to be careful about the global batch size and learning rate. So usually what I do is that first I just try to scale the global batch size and learning rate proportional to the number of workers. The theoretical kind of consideration behind that, you can check the talk that I gave in the Apex. But basically say that if the batch size, when you're doing single GPU is, for example, 16. Now you do like in 1000 GPU, you just keep the local batch size the same, that's 16 per GPU, right? And then that means that global batch size will be 16 times 1000. And learning rate also just scale linearly versus the number of workers. And that typically will cause some trouble in the beginning of the simulation, because when you have large batch size and large learning rate in the beginning, it's very hard to stabilize because of the learning rate essentially the step for you doing optimization. If your step is too large, then you're just wandering around, cannot find the local minimum point. So a trick to do that is that in the beginning several epochs, you reduce the learning rate, use a smaller learning rate, and then later on increase to a larger learning rate. And so this is the kind of, you can try this. If this work, then perfect. Okay, but most of the time this doesn't work out of the box. So actually this learning rate and global batch size is a kind of hyperparameter. So you in large scale, you might need to tune this learning rate and then the global batch size kind of adjust a little bit and to see to get a better convergency. And yeah, so this is a case by case. So I currently, according to my experience, there's really no kind of a suggestion. So you just check the convergency. If it is doesn't converge well, reduce the learning rate, reduce the batch global batch size, right? And okay, and then another thing, this is to avoid unnecessary communication overhead. So I've seen that some people usually they want to know that the loss at each time step. Of course, when you do the single GPU training, the GPU it will calculate the loss from each GPU, right? Now you do the distributed training. In order to know the loss, you have to adding up all the loss from all the GPU. But you don't have to do that at every time step, because that will cause some communication overhead. Because each time when you add up all the loss, it will introduce these introduce the communication overhead. So a lot of metrics like accuracy, loss, just do that at the end of each epoch. Then the communication overhead will be small. Okay, and just to give you a sense about what kind of scaling efficiency we will get when you scale up this application. So I provided two examples here. One is ResNet 50, which is kind of every people know. And the other is Cosmos Flow. ResNet 50, I scale up to 1000 A100 GPU. I got pretty good scaling efficiency, 91%. And Cosmos Flow, ResNet 50 was using TensorFlow plus Huihuo. And Cosmos Flow, this is PyTorch plus DDP. This is it's more kind of compute intensive, so the scaling efficiency is pretty high, 99%. And then you might wonder, now I have like several framework, Huihuo, DDP, DSP, which one perform better, right? According to the test that we did, this is from the intern students working with me during the summer, we found that actually they are pretty similar to each other, at least now. Maybe a couple of years ago, some of the framework performed better for some special cases, but for now, what we found out according to the workload that we test, it is kind of similar to each other. But you can try and let me know if you find like one distributed framework work better for your application, and that would be good for me to know. And then next time I can tell the users. And okay, I want to mention, take like about 10 minutes to mention about the data management and I/O. This deep learning has like significant different kind of I/O pattern compared to the traditional HPC workload. HPC, usually you deal with a large chunk of data, like multi-dimensional array, and mostly it is kind of write intensive. Basically, you do like iterative base of simulation, and then you do the checkpointing at each time step. And so it's write intensive, and it's more kind of large bulk of data, and it's usually like binary data. And then the traditional, you may say that the storage system or file system was kind of designed for that. Now with the deep learning, it's kind of, the story is different. Deep learning is read intensive because every epoch you need to read the entire data set once. And then also metadata intensive because usually the data set is kind of saved in millions of small files, and that places a lot of burden on the metadata server. And then in terms of the I/O, I see that many times was the sample size very small, so you're kind of loading small I/O, and it's also involved random access because of the shuffling. And then in terms of data format, we have like binary format and text format, JSON files. So yeah, a lot of kind of interesting things to learn how to optimize this I/O for deep learning application. And another case is also the multi-threading. So usually in the deep learning training, you use multiple I/O worker to load the data concurrently in order to feed the data to the accelerator to do the training. We've done a lot of kind of study. We also create a benchmark to learn all those kind of characteristics for deep learning. If you're interested, you can check this link here. I just provide some example that to give you a sense about the complexity of the I/O and how what are the things that you need to be aware of. The first example here I show is the single node. In the single node case, this hasn't been kind of doing a distributed training case. Actually, I distributed across the 4 GPU on Polaris. And there is one thing that adjusting parameter in the training in the framework is called the number of worker. This is in PyTorch number of worker, and then in other cases will be like maybe the number of thread. This is for data loading the data. So the case I show here is for PyTorch. You can see here, by default, this number of worker is 0. And that's, I think a lot of users just not tuning the number of worker. So using the number of worker equal to 0. The 0 means that you don't use any background thread to load the I/O at all. So basically you do the training, you load the data and then do the training, load the data, do the training, no overlap at all. And this is very inefficient. And especially in this case, the I/O is kind of 4 times more than the training. So if you don't have the overlap of the I/O and compute, this is the total time per epoch. It's 90 seconds per epoch, right? A simple trick to optimize this is just use more number of worker. So here I use 4 worker. So the master thread just continue to do training, and the worker I/O worker or I/O thread just load the data and feed it to the master thread to do the training, and that can improve this significantly by 4 to 5 times. right? So remember, always try to use multiple workers to kind of minimize the I/O overhead. Okay, second thing is the this I even myself just learned it recently, is the CPU binding is significant to this training. So by default on Polaris, if you don't use CC depth or any kind of CPU binding, it will just put all the thread on a single CPU. So that create a big problem. In the case here, as without the CC depth, this is with the CC depth. If you have the CC depth and then specify the distance, basically make sure that those I/O threads are placed in different CPU cores, and that improve the performance also significantly. As you can see here, this is without also 5 times difference. So this is another kind of important thing to be aware of. So all of this on a single node level, and then on a multiple node, when you scale it up, okay, we mentioned that the communication overhead, the all reduce will cause the scaling bottleneck, right? As you run into large scale. And recently what I'm seeing is that the I/O can also potentially cause the scaling bottleneck. In the case that I show here is a UNet 3D. It's very I/O intensive. The sample size are very large, and then so when I scale it up to 100 or 200 nodes on Polaris, I found that the I/O throughput cannot, because it's a kind of theoretical peak bandwidth that can be provided by the Lustre parallel file system on Polaris. So I think after I scale up to 100 nodes, it's already hit the bandwidth. I mean, hit the bottleneck that Lustre can provide. So that caused the scaling efficiency dropped. So one trick is that you can use the NVMe, the non-local storage, so basically you just move the data to the non-local storage and do the training on the non-local storage, and then you can keep scaling. So this is another trick if you have heavy I/O on your training. Okay, and then there are a few other tips. I probably don't have too much time to go through each of them. I'll just mention briefly. First is to make sure to save your data in a binary form if you can, not in a text format, right? Because that will reduce the amount of I/O significantly. Second thing is always consider how you organize your data. Sometimes you want to organize the data with file per sample. Sometimes you want to put everything into a single share file, or sometimes you want to do in between, like a few sample per file, right? And try that, and also make sure to play with the larger strike counts and step size to give a kind of better performance. And yeah, and a lot of data loader support prefetching and caching. So play with that to see whether you can improve your I/O performance, and using more I/O worker that I mentioned in previous slides. This is the kind of data loader that you can use to have some kind of advanced feature. One thing is that I mentioned you can use multiple I/O worker, right? But with PyTorch, currently there's a limitation on Polaris. So if you use number of I/O worker greater than 0, and then you scale it up to multiple nodes, it will cause hang. A lot of time it will cause hang. And so on PyTorch, basically if you scale it up, you can only use number of worker equal to 0, right? So one solution is that you can use DALI data loader, because DALI data loader also support PyTorch, and then it uses the different kind of thread create spawning mechanism. So that using DALI data loader, you can use multiple worker without causing a hang. Okay, this is the lesson. Okay, I think this is the link to the hands-on example I just list off here. You can play during the break and then let me know if you have any questions afterwards. Okay.
Thank you, Huihuo. We have time for maybe 1 or 2 questions if anybody has them.
Nice talk. You talk about the global scaling batch, size of trend, the learning rate. Now I know conventionally when you want to do the training, you allocate the greater portion of percentage, maybe 80% for training and 20 maybe for testing. Now, how will you be able to normalize the global worker number, the number of workers against the learning rate, so that the proportion will be the same in order not to have a problem? How will you be able to achieve that?
So you're asking the relationship between the batch size and the learning rate, right?
Yes, because you say that if you are not able to have a better proportion of the workers on the learning rates, you may likely have issues with the learning rate while training it. So I really want to know, how do you achieve that by making sure that the workers and the learning rates are in the same proportion?
Okay, yeah, we can talk more afterward, but basically just this first trial, I mean, you can drive it just proportionally. If you scale up global batch size, you scale the learning rate proportionally. And then later on adjust the learning rate or global batch size according to the conversion behavior.
One more question again. For the the use of DALI loader?
Yeah.
So you said it's preferred compared to using PyTorch?
Compatible, yeah, compatible. DALI support the PyTorch framework.
Okay.
Yeah. Any other question?
All right, if not, let's thank Huihuo.